Hello everyone and welcome back. So last class we were looking at the mass transport losses and what their significance. So we started with the concept understanding of how this hydrogen or the species flow through channels as well as the diffusion layer, and we saw that through these channels the flow is through the convection as well as through this diffusion layer. The flow is through diffusion because the hydrogen basically diffuses through this gas diffusion layer and then reaches the catalyst layer. So, the concentration of hydrogen in the flow channel is at this level as marked by CH2, and as and when, since we are drawing a lot of current from the cell, the concentration gradually decreases as and when the hydrogen passes through this diffusion layer, and it is at the interface it is C0HT, that is concentration at the interface for at a given time t, and this we have assumed it to be C star H2. So, let us move on. So, this thickness, so the thickness or the distance basically in which the diffusion dominates the convection is the diffusion layer thickness. It is denoted by delta, and as you can see it is quite tough to define where this actually diffusion layer thickness is and where it actually starts. So, this delta is difficult to define as in reality you cannot distinguish the convective and diffusive transport. And one thing we have to very clearly understand that this delta is not equal to gas diffusion layer thickness. Okay, since this GDL thickness, let me write as T GDL, is defined or it is fixed for a given cell configuration. What it means, in other words, is once we choose a particular catalyst or once we choose a gas diffusion layer for a fuel cell or electrolyzer, the thickness is already defined. So, this delta is not equal to the gas diffusion layer thickness. If I try to simplify, let us say we are operating at atmospheric pressure. So, this is the hydrogen through channels and this is its concentration in the channels, and this is C star H2. So, this diffusion layer, this delta is, in this case it is x microns. However, if we increase the pressure to, let us say, 2 atmosphere, now the pressure of hydrogen is doubled. It is still flowing through the channels. However, in this case the diffusion layer thickness will be smaller compared to x microns. So, in this case let us say delta is y microns, this is again CH2 and this is C star H2. and if you increase the pressure to, let us say, 5 atmosphere, this delta will further decrease. Now, this is the delta. So, I can say that, so this is P1, P2 and this is P3. So, P3 is greater than P2 is greater than P1. In that case, so this delta, which is Z, in the third case Z microns is smaller than Y microns is smaller than X microns, and this is not equal to thickness of the gas diffusion layer, it is fixed. So, let us draw that figure one more time, this time a bit complicated. So, this is the distance, this is flow channel, this is a complete electrode, I would say, which also takes into account the flow through diffusion. So, let us take the concentration on y axis, and this is my CR, it is bulk concentration of the reactant species. It is equal to the same value at the electrode surface itself when T is equal to 0. In other words, when we are not drawing any current from the fuel cell, the concentration at the triple phase boundary is also same as that of the bulk concentration. So, this is my catalyst layer. So, as and when the time increases, let us say this is T1, then this is a T2 and this is say T3, and when T becomes T infinity, so this is T infinity, this is T2, this is for T3, then we get the local concentration or the concentration of reactant at the catalyst layer as CR star. What is happening with respect to the product species? Product species initially, when there was no current being drawn or when T equal to 0, the concentration of product was almost 0. However, with increase in time or with respect to time, this is again T1, the concentration of Cp also started increasing. This is T2, then T3, and when T becomes T infinity, this is T infinity, this is Cp star. So, let me write that up as the reactant species diffuse towards the catalyst layer the product species diffuses out at the steady state, depletion of reactant species is equal to generation of product species. Okay. So, when the steady state reaches, the concentration of reactant species at the rate which they are getting depleted is same as that of the concentration of product, at the rate when they are getting generated. So, this is at the t equal to infinity, and this again this is our diffusion layer thickness delta, that is where the concentration differences occur. So, let me go ahead and write this up. At steady state, consumption is equal to supply, right. So, let us talk in terms of the current density. So, current density is N F. Let us define one more parameter, J, a subscript diff. So, this is our current density, and this N and F are already known to us. J diff is basically diffusion flux of species to catalyst layer, and this is same as that of the, or I can say, diffusion flux of product P from catalyst layer. So, how can write this diffusion flux? So, diffusion flux if is minus d times dc by dx. So, this d is basically diffusivity of a particular material. In other words, how easily a gas can diffuse through the diffusion layer. So, that is determined by this diffusivity, and dc by dx is basically concentration gradient at that diffusion layer thickness. So, I can write this as, so this diff is, I can write d effective, and what is the concentration difference? It is Cr star minus Cr by delta. What is the Cr star? That is the catalyst layer reactant concentration, and Cr is bulk concentration, or the concentration which we supply, which is available at the in the channels of bipolar plate. I can also write this as available in the flow channels. What is this d effective? This is effective reactant diffusivity. So, let us put this back in the current density equation. So, we can write current density as Nf, this d effective Cr star minus Cr divided by delta. Yeah, so we have not put up negative sign here. That is because the negative sign merely signifies that this, as and when we draw more and more current, the Cr star basically decreases with respect to Cr, or in other words, this diffusion layer also changes accordingly. So, I can write this up as in the form of Cr star is Cr minus J times delta divided by Nf d effective. So, what does it imply? It implies that as Cr star is less than Cr, and as this current density increases, increases, the surface concentration decreases, or in other words, higher is the current density, or in other words, if you are drawing more and more current from the cell, severe concentration loss will be incurred. However, if diffusion layer thickness which is delta decreases, or by some means if we decrease the diffusion layer thickness, the surface concentration will also increase, and correspondingly the concentration loss will also be decreased, right. So, if we know that more and more current if it is drawn from fuel cell, what does it imply? It implies that the surface concentration will be almost 0. Why there will be a surface concentration 0? Because as there will be no reactant spaces available, or there will be no reactant spaces left for more convergence to product. So, what does it imply? That implies J is equals JL. We are introducing a new term here, which is an FD effective CR by delta. And what is this JL? JL is nothing but limiting current density. What does that mean? It is the maximum current that can be drawn from a fuel cell at a given flow rate of reactant species. So, what does it mean? Let us draw a characteristic curve. This is J and this is JL, there is a limiting current density. So, as or J approaches JL, in other words, as and when we draw more and more current from the cell and approach the maximum current that we can draw, the potential almost reaches 0 volt. And why is this happening? Because as and when we draw more and more current from the fuel cell, we are basically converting hydrogen into protons and respective electrons, and they are quickly consumed at the catalyst layer. So, there is no hydrogen left for the further conversion into protons and electrons, and that is why the potential drops drastically, and that is what happens when the current is almost reaching to the limiting current or limiting current density. Now, in other words, should we not draw maximum current, or should we not draw limiting current from the fuel cell all the time? So, let us discuss that. since the function of fuel cell is to supply more current. As we know that power is nothing but product of potential and the current. So, more is the current, more will be the power. So, more current. So, this has to be without much compromise, okay, on potential. So, you have to make sure that the potential also is significant and the current that we are drawing is fairly large, then and then only the power output from the fuel cell will increase. So, how we can do this? This can be done by better value of current density. More is the value of current density, more is the potential for us to basically draw the current. So, better is the current density, better will be the output. And how we can achieve this? The surface, the bulk concentration should be high. So, how we can do this? Some bulk concentration of the reactant should be fairly good or fairly large. And how we can achieve this? By employing a good flow structures. So, we should have better flow structures to be employed. So, we will discuss more about flow structures in the upcoming sessions. Second, what should be better? Effective diffusivity should also be better, is high. Third, the diffusion layer thickness, let me write that down. Diffusion layer thickness should be minimum. So, how we can do that? By pressurizing the reactants, we can see that the diffusion layer decreases, and as and when it decreases, we can increase the limiting current density. So, if we try to see the characteristic curve of a typical fuel cell, let us say this is the characteristic curve obtained for the flow rate of, let us say m dot h2 is 1 lpm. So, does it mean that by increasing the flow rate of hydrogen and subsequently oxygen to fairly large values, can we eliminate the concentration losses? Let us say this is m dot h2 for 1 lpm. What happens if this m dot h2 is, let us say, 2 lpm? So, as we can see, this flow rate and its effect basically comes into picture typically in the third phase. So, let me use the different colors. This is, let us say, for 2 lpm, the characteristic curve will fairly remains the same. So, let me overwrite this. However, it will go and have, so this is my JL for corresponding JL for 2 lpm flow rate, this is JL for 1 lpm, and what if my JL is increased or flow rate is increased to, let us say, 3 lpm, still the IV curve will fairly remain same. I am just trying to draw this separately, otherwise theoretically all these curves will overlap at least till the ohmic zone, and then it will remain straight. So, this is here. So, what does it imply? It implies that no matter how high we make the flow rate of reactant species, that is hydrogen or oxygen, we cannot achieve infinite amount of current, or we cannot draw infinite amount of current. The primary reason for that is basically the current that we are drawing from the cell is limited by the inherent resistances of individual materials. For example, we have activation over potential, that is the resistance offered by the catalyst layer itself. Then we also have the ohmic over potential zone in the second phase. So, even if we supply more and more fuel, in the first place we will be also losing the fuel efficiency, as we have discussed this in the previous sessions. And secondly, despite supplying more and more flow rate, we can see that it will still hit the x-axis somewhere here. So, the over potential or the mass transfer over potential in this or the higher over flow rates will be minimum, it will not be eliminated. So, we have to very wisely choose the flow rates of these reactant species, that is hydrogen and oxygen, such that we do not lose much upon the fuel. At the same time, we also do not end up in the mass transfer over potential. So, we will take on with the upcoming sessions with the more on this mass transfer over potential in the next class. Thank you.